Bismillahirrahmanirrahim. Dear students, in this week we will be solving some more problems related to shear force diagram, bending moment diagram. So let's start with our first example. Example number one. And this example is related to a simply supported beam subjected to a VDL. Span of the beam is 10 meters. We will have two reactions here, 10 meters. Magnitude of 10 kilometers. And if you call this fluid as A and this fluid as B, so this reaction will be RA and this will be RB. Okay, so in solution of any beam, as we have discussed earlier, the first step is to determine the reactions of the beam. So let's start with reaction calculation. And as it is a determinate structure, so we will apply conditions of equilibrium to get reactions. So first let's apply sigma Fy equal to 0, and our convention will be that upward forces will be taken as positive. Okay, so how many upward forces are there? Ra acting in the upward direction, so it's positive, plus Rb. We have assumed these reactions to be in upward direction, so both are positive. And then this VDL is acting in the downward direction. Now the resultant of VDL, as we discussed in our first class, that resultant of VDL passes through the centroid of the triangle and direction will be downward in this case because the load is acting in downward direction. So if I know the resultant here, it will be somewhere over here, resultant R, and N is this ordinate and 10 is the base. So 10 into 10 divided by 2, and this gives us 50 kilometers. So the resultant of this VDL is 50 kilometers and it will act at a distance of 10 by 3 from this. 10 by 3. So we have resultant whose magnitude is equal to 50 kilometers and it acts at a distance of 10 by 3 from point B. Alright, so now let's come back to the equation. So Ra plus Rb, and then this 50 kilonewton force is acting in the downward direction. So minus 50 is equal to 0. And if I rearrange this, I get Ra plus Rb equal to 50. Now in this equation, we have two unknowns, so we cannot proceed with the solution. We will have to generate one more equation. So for that, let's apply sigma mb equal to 0. Sigma mb equal to 0, and our convention is we will take clockwise movement as positive. So let's start from this side. Now Ra is producing movement in clockwise direction about point B, so it should be positive. We do not know how much is the magnitude of Ra, so Ra into 10. And then this resultant 50 kilonewton force, and it will produce movement in counterclockwise direction. So minus 50 into 10 by 3, 10 by 3 is the limit arm, and this should be equal to 0. So we have written the equation of sigma mb equal to 0, and we have only one unknown in this equation, and that is Ra. So if I solve this equation, I get Ra equal to 16 to 16.5 16.67 kilonewton. So this is the value of RA. And if I plug this value in equation number 1, I get the value of RB. RB is from equation number 1. If I plug in RA into 16.67, I get RB equal to 33.33 kilonewton. So this is the value of RB. So in this way, we have calculated both the reactions RA and RB, and next step is to divide the beam into a required number of portions. We have discussed that we divide the beam into portions whenever we see any variation in loading, or like any abrupt variation in loading, or any change in support condition. If you look at this problem, the load is gradually changing throughout the beam. There is no abrupt change in the applied loading, and we have one support at one end and other support at the other end. So this entire length of the beam can be considered as one portion. So in this case, our portions will be, there will be only one portion AB, and we will consider one section in this portion AB, and that section will be at distance x from support, because our convention is we always move from left to right. That's the convention that we are following. Okay, so let's consider portion AB, and the value of x will vary from 0 to 10 meters. Now let's draw the free body diagram of this portion. 0 is point A and 10 meters is point B. So if I want to draw the free body diagram, I will have to consider either the left part of the section or the entire right part of the section. And our convention at this stage is that we will always be considering the left part of the section. So let me draw the free body diagram. We have a hinge support here. And we know the reaction at this point A. Reaction is 16.67 kilonewton. This median is acting in the downward direction, and as we have exposed the section, so we will have shear force here and bending moment here. M. What else? This distance is x. This is x. Do we know this height? How much is this height? We know, in case of beam, we know that the VDL is 0 here and it is 10 here. But if we cut the section at any intermediate stage, do we know how much will be the ordinate at that location? I think we don't. We do not know how much is this. So let's call this as y, and we will try to calculate how much is this y. Okay, because when we will be calculating the shear force for the left side of the section, means for this part, then we will need this coordinate, because in order to calculate the magnitude of the resultant for this triangular load, we need to see how much is this coordinate. We will multiply this coordinate with x and divide that by 2 to get the area of this triangular part, and that will give us the magnitude of VDL. So we need this coordinate. Now, how to calculate this coordinate? For that, we will have to use the concept of similar triangles. Okay. Now, let's see. If I look at this diagram, we have this bigger triangle, and then by cutting the section, we have generated a smaller triangle. And these two triangles are similar triangles. Let's see how. we have this point is A, this point is B. Okay, I'm just following the same convention. Let's say I call it C, and I have cut a section here. Let's say, right, and let's call it as V, and let's call it as W. Now we have a bigger triangle ABC, and we have a smaller triangle AWV. And if we consider both these triangles ABC and AWV, do we know the side AB? How much is side AB? It is 10 meters. Do we know AW? According to our nomenclature, this AW is X. Do we know CB or BC? This is 10. And what do we want to calculate? We want to calculate this Y or VW. So from similar triangle concept, this the ratio of base of this triangle and perpendicular. So AB over BC should be equal to AW over VW. AB over BC should be equal to AW over VW. And how much is AB? We know AB is 10. How much is BC? BC is also equal to 10. What is AW? AW is X. What is VW? VW is Y. So if I rearrange this equation, I get Y is equal to X. So for our given situation, uh, if we consider these two similar triangles, we get Y is equal to X. So this Y is equal to X. Now for this loading, we know the base of the triangle as well as the perpendicular of the triangle. So we can calculate the magnitude of the load. Now let's move towards writing down the equations of shear force and bending moment. For shear force, we will write down the equation sigma Fy equal to 0, and our convention will be we'll take upward forces as positive. Now, how many forces are there parallel to y-axis? We have 16.67 kilonewtons. So it's acting in the upward direction, so it will be positive 16.67. Then, what about the resultant of this triangular load? We mark the resultant here. It will be, let's say, acting somewhere over here, and the magnitude of the resultant will be x into y divided by 2, and we have calculated y equal to x, so it will be square divided by 2. And how much will be this distance? This distance will be x by 3, because the base of the triangle is x. So from this side, the location of the centroid will be x by 3. So 16.67, and then this r is acting in downward direction, so minus x square by 2, and then this v is also acting in the downward direction, so minus v, and this is equal to 0. And if I rearrange this equation, this implies v is equal to 16.67 minus 0.5 x square. Okay, if I call this equation as equation number 2, and I call this equation as equation number 3. So from this equation number 3, this is the expression for shear force for the entire beam. Now we need, as we can see that x is involved in this equation, which means that shear force is changing throughout the length of the member. So we will have to calculate it for point A and point B. So at A, x is equal to 0. At point A, x is equal to 0. So this implies V is equal to 16.67 minus 0.50, and this is equal to, like this is u square, 16.67 kilonewton. And at B is equal to how much? X is equal to 10 meters. So this implies B is equal to 16.67 minus 0.5 into 10 square, and this gives us minus 33.33 kilonewton. So in this way, we have calculated the magnitude of shear force at point A and at point B. Now let's move towards the bending moment and write down the equation for bending moment. We take sigma mx equal to 0, and our convention will be we take clockwise moment as positive. Okay, so how many forces are producing movement about this section? Let's start from this side. 16.67 kilonewton. It is producing movement in counterclockwise direction, so it should be taken as positive. 16.67 lever arm is x, and then the resultant of this median is x square by 2, and it will produce movement in counterclockwise direction, so it should be taken as negative. X square by 2 is the magnitude of the force, and the lever arm is x by 3, as we have already mentioned it on the diagram. X by 3, and what else? This m is also present here, and m is in counterclockwise direction, so minus m, and this should be equal to 0. And if I rearrange this equation, I get m is equal to 16.67 x minus cube over 6. This is the equation of bending moment for portion AB, right? If you want, you can simplify this further. 16.67x minus 0.167 x cubed, and we can call this equation as equation number 4. So this equation is showing the bending moment variation in portion AB. Now next step is to plug in the value of x for point A and point B to get the value of bending moment at point A and B. Let me do it. At point A, x is equal to 0. This implies m is equal to 16.67 into 0 minus 0.167 into 0 cube, and this gives us 0, right? And is this 0 logical? What do we have at point A? At point A, we have a hinge support. Okay, let me see, my ballpoint is giving me trouble. All right, let me change my pen. All right, so we have this 0 here, and this is hinge support. So this 0 is logical. Now let's move on and calculate the value of moment at point B. At B, how much is the value of x at B? X is equal to 10 meters. So this implies m will be equal to 16.67 into 0 minus, into 10 minus 0.167 into 10 cube. And if you solve this, you will again get, And this 0 is logical because we have a roller support at this point. All right. So in this way, we have got the value of bending moment for both points, point A and at point B. But apparently, the entire bending moment diagram seems to be zero because the bending moment at the starting point as well as ending point uh, are equal to zero. Bending moments are zero at both these points. Uh, but we will have to draw the shear force diagram, and then we will see that whether we have a zero shear point somewhere in the shear force diagram. If we do, we will calculate bending moment at that point, and we will get some value bending moment. Bending moment will be maximum at that location actually. Okay, so let's start drawing shear force diagram and bending moment diagram. Okay, all right, let me draw the beam here once again. So we have a simply supported beam subjected to a VDL which is 10 kilonewton and is 10 meters. We have one reaction here. This point is A. This point is B. RA we have already calculated. It is 16.67 kilonewton and RB we have also calculated. And how much is RB? It is 33.33 kilonewton. And now we want to plot shear force diagram and bending moment diagram. So let me draw the guidelines. Here are the guidelines for SFD and BMD. Okay. This is our 0, 0 line. We want to draw SFD and the units are kilonewton. Okay. How much is the value of shear at point A? It is 16.67. 16.67. And how much is the value of shear force at point B? It is 33.33. And as I mentioned earlier, that this diagram, all these diagrams are drawn on rough scale, not on exact scale. So we have these 2 points, 33.33. Now the question is that how should these 2 points be joined? Should these be joined with a straight line or with a curved line? If it's curved, then whether it should be convex up or concave up. So there are several questions. So for these questions, we will go to the equation of shear force. Now here is the equation of shear force. This equation number 3. This is the equation of shear force for this portion. Now, what is the degree of the equation? The degree of equation is 2. So it means that we will have a second degree line joining this point to this point. And whether this second degree line will be convex up or concave up, this answer will come from the load, the applied load. If the magnitude of the applied load is increasing, the slope of shear force diagram should also be increasing. It's exactly the same the way we did it for bending moment diagram. When we in last class when we solved a problem for bending moment diagram in which bending moment diagram was second degree, so we looked at the magnitude of shear force. So if we are drawing bending moment diagram here, then we look at for the slope of bending moment diagram, we look at the magnitude of shear force diagram. And for the slope of shear force diagram, we look at the magnitude of bending moment diagram. So here, the magnitude of load diagram. As the magnitude of load is increasing, so the slope of shear force diagram should also be increasing. And how do we draw the increasing slope? It is drawn like this. So it is convex up. The slope here is very small. It is a small magnitude. But if I draw a tangent here, then this is the correct, the correct orientation of shear force diagram for this situation. And we will have to write down the degree. This is second degree, because when we have curved line, just by looking at the line, we cannot judge the degree of the line. So whenever you will draw a curved line in shear force diagram and bending moment diagram, you will always write down the degree of the diagram, degree of the line. So this part is positive and this part is negative. And we will have this. This completes the shear force diagram. Now, in this diagram, we have a point of zero shear. So we will have the value of maximum bending moment at this location. And for this, we will have to calculate this point. Then, how much is this point? And calculation of this point is simple. We will simply see the equation of this part, this portion. The entire beam is one portion. And in that equation, like this equation number 3, this is the equation. We will put that equation equal to 0, and corresponding to that we will calculate the value of x, and that will be this location of x for which the shear force is equal to 0. So let me write it down. So V is equal to 16.67 minus 0.5 x square. So just put it equal to 0. We are doing this calculation for point of zero shear. Point of zero shear. So if we put it equal to 0 and you will go through the calculations, let me give you the value of x directly. So this equation will give you x equal to plus minus 5.77 meters. Now, the minus value of x is illogical in this case, so we will just consider the positive value of x. So x is equal to 5.77 meters in this case. It means this distance is 5.77 meters. So if this distance is 5.77 meters and we want to draw a bending moment diagram, we will calculate the value of bending moment at this location. So for that we will have to consider equation number 4. This equation number 4, which is the equation of bending moment. So m at x equal to 5.77 meters. So m is equal to 16.67 into 5.77 minus 0.167 and 5.772. So if we solve this equation, we get the value of m as 64.11 kilonewton meter. So here is the value of m at x equal to 5.77 meters. So we have got the ordinate of bending moment diagram at this location. It is 64.11 kilonewton meter, and this is 0, 0 line. We are drawing bending moment diagram, and our units are kilonewton meter. Now again, we need to see that how we should join this point with this point. For that, again, we will look at the degree of the equation. If we look at this equation, degree of equation is what? Degree of equation is 3. So these points will be joined together through a third degree line. And whether that third degree line should be convex up or concave up, answer of this question will come from magnitude of shear force diagram. As the magnitude of shear force diagram is decreasing in this direction, so the slope of bending moment diagram should also be decreasing. We have a third degree line whose slope is decreasing. It has some slope, or it has maximum slope at this point and it has minimum slope at this point. And for the remaining part, again we will look at the magnitude. Magnitude is again increasing, and I'm talking about the absolute magnitude. Like I'm not talking about the negative or positive. So if it is increasing, then the slope of bending moment diagram should also be increasing. Let me draw it. Somewhat like this. So the slope of bending moment diagram is increasing and this part is again 30 degree. And the entire bending moment diagram in this case is positive. So if the bending moment diagram is positive, it means that the beam will sag down. So the last part of our problem is always to draw elastic curve of the beam. So let me, the entire bending moment diagram is positive, the elastic curve will be like this, sagging throughout the length. This is elastic curve of the beam. So this completes the problem. We have drawn a shear force diagram, bending moment diagram, and elastic curve. All the important points have been labeled and calculated. So that's it. I will just stop recording here. Thank you.